Good afternoon. Hopefully, you've all taken out the opportunity to take a look at Module 7, Investigation 3, Problems 3 and 4 before we get started with this video so that you've got some things to kind of think about as we move through them. The goal today is to get through this slide as well as the next slide because those two will help you to finish up your Module 7 and 8 Homework 1, which is due on Friday, November the 1st at midnight, or 11:59 p.m. rather. So hopefully these two will give you a hand. So I'd like for you to, if you haven't already, to pause and take a moment to look at problems 3 and 4 on Module 7, Investigation 3, and see what you can do with them. The first problem asks you to, the first problem asks you to consider a point XY on the circle. So suppose that we choose this point, I don't know, this point right here. This is the point XY on the circle. And what it's asking us is to consider the angle theta and the sine of theta as we have defined it previously. So we've got, so if we swing an arc, we swing an angle out all the way to XY, then this right here is theta, right? That's terrible handwriting, pardon me. I'm on my computer at home and the screen is somewhat slick. It doesn't matter, whatever. So the, and then sine of theta, remember sine of theta was defined as the vertical distance above the horizontal diameter. In fact, we defined it this way, that V is equal to R times the sine of theta. And so that means that the sine of theta should be V divided by R. Well, the radius in this particular case is just 1. So that's helpful because we know that because it meets out at 1, 0 and all that kind of thing. So V divided by R would just be V, or this vertical distance right here. Oh, sorry about that, guys. Let's go back. Would be this vertical distance right here. My hand touched the side of the screen there. So this V right here is what we're looking for as the vertical distance or the sine of theta. So what we've got here is the sine of theta is this horizontal, or excuse me, this vertical distance here. And then in problem number 4, it asks us to consider how the bug's horizontal distance, so we got Larry the stink bug is back, horizontal distance to the right of the vertical diameter, how that changes as the bug travels from the 3 o'clock position to the 12 o'clock position, the 12 o'clock position, the 9 o'clock position, blah, 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 right? All that stuff. So, so let's take a look here. So, in fact, I think what I want to do is I want to take this guy here and I want to expand him just a little bit. I want to make him a little bigger. Let's pull him out here. Let's make him a little bit bigger so that I can look at him a little bit better. So the horizontal distance to the right of the vertical diameter. So the vertical diameter is right here. Not very straight, but that'll work. There's our vertical diameter. And the horizontal distance to the right is what we're looking at. We'll call that H, okay? H is the horizontal distance to the right of the vertical diameter. So that's going to be H in this case. And of course, if we call H the horizontal distance from the vertical diameter to the right, then that means that all the distances to the left of that would be negative H, right? Those would be negative H values. So if we kind of sketch in Stinky's path around here, and we want to look at like his position right here, right? Then we could extend this line out. This would be H that we're talking about. So as we go from the 3 o'clock position to the 12 o'clock position, we're moving from being as far from that vertical diameter as we can get to sitting right on it. So unlike on the sine function, we were getting further away. This time we're actually getting closer. So we're starting from 2.6 feet away to 0 feet away, which means that the change in H would be negative 2.6 because we're decreasing 2.6. And I've given us a little chart over here to notate that. So I'm just going to go ahead and start filling that in. So we've got negative 2.6 as our change in H there. So that's in that first quarter turn. So from 0 radians to half pi radians, which is right there at the 12 o'clock position, we've got a change of negative 2.6. From the 12 o'clock position to the 9 o'clock position, we go from 0 feet to, okay, now if we end up over here, then this distance in here, because it's to the left instead of to the right, is going to end up being negative 2.6. So to negative 2.6 feet. So there is another decrease of 2.6, or a negative 2.6. Okay. From the 9 o'clock position over here down to the 6 o'clock position, that means that we're going to be going from being at negative 2.6 back to 0. So that's a change in H of positive 2.6. And then the same thing is going to happen as we move from the 6 o'clock position back over to the 3 o'clock position. We're getting further away from that vertical diameter, so that change in H is going to be positive 2.6 again. So we've got 2.6 and 2.6. And you can tell that this is really just a rehash of the sine problem that we did in problems number 1 and 2 from this investigation. And so what we've got is this change in position. So if we wanted to create a graph to illustrate the bug's position, we can do that. I'll change my color here. If we want to do that, we can. So let's say that I go from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. I don't think these are really evenly spaced, but we'll let it happen. We can only get a maximum of 2.6 feet away from that vertical diameter in either direction. So what we've got here, and I probably should have labeled this before I started, is the angle again. And then here, we're notating the value of H. And that's just terrible. Let's try that again. Oh, goodness. Let's go this way. That'll work. Okay. Okay. So at 0, right, at the 3 o'clock position, I am 2.6 feet from the vertical diameter. At the first quarter rotation, right up here at the noon position, I am on the vertical diameter. Once I move around here to the 9 o'clock position, I am negative 2.6 feet from the vertical diameter. As I move around to the 6 o'clock position, I'm back on the vertical diameter. And then as I move back to the 3 o'clock position, in other words, I've made a full 2 pi rotation, I am again 2.6 feet from the vertical diameter. So this looks very similar to the sine curve, only most of my students want to do this, right? But we already talked about the fact that that doesn't make sense. It doesn't make sense to have straight line movement because we know this is not a linear function. We don't have that constant rate of change. So we are going to do the same kind of thing we did for the sine function, and we are going to look at the variance. And this is not as beautiful as it would be if I drew it on the board, but here we are. That's okay. So this is our function. This particular function is known as the cosine function. So just like we studied before that we had the sine function, here we have h is equal to r times the cosine of theta. And when, in this particular case, theta is measured in radian measure. All right, cool. So that gives us the cosine function to add to our sine function. And on Monday, at the beginning of class, we will add that to our Microsoft Word document so that we can add that into the rest of our trig functions. So putting some of this together, because the cosine function is going to have exactly the same features as the sine function that we've already talked about. You can change the radius, you can change the speed, you can change the placement of that vertical diameter, just like we could change the placement of the horizontal diameter. And we'll have some examples that do those kinds of things as time moves on. What I want to do here, because this kind of problem is also in your homework, I want to make sure that we are feeling good about this. So this function, the function f that's in this graph here, there's an end result down here, which is to define a formula for the function. And so it's going to ask us some questions leading up to that. And this would have been prep work, actually, for Monday, or maybe even for today. It would have been prep work for today, but I decided that I'd rather just go ahead and kind of talk you through it. It's in the, I think it's one of the last homework problems on the Module 7 and 8 homework assignment. So I want to give you some good lead up to that. So first of all, this particular function, like when we're on this vertical axis here, we are starting right here. And you can see, in fact, I'm going to change, let's change pens again. Let's do a highlighter. We are changing from here and up, down, and back up. Okay. So here's a full rotation, if we were going to mark it as a full rotation. So here's the deal. You could actually write this as a sine function or as a cosine function. Honestly, you could do it either way. There's legitimacy to both approaches. And we will talk more in class about how you could write it both ways. But for right now, we're going to use it as a sine function because we can see that sine curve pretty easily. So if I use this as a sine function, the period would go from here to about here, a little bit more than 4. Now, the book actually has a specific value that they want you to assign to this, but they're insane because they didn't mark their axis using any kind of terms of pi. So I'm not going to try to do that. That seems crazy. So instead, I'm going to say the period is about 4.2. Okay, it's about 4.2. The minimum value is down here at -7, and the maximum value is clearly up here at +3. Those are pretty easy, right? What is the equation of the horizontal line that falls halfway between the function's maximum and minimum values? In other words, the midline. So the midline is going to be right here at -2. We could get that a couple of different ways, but if we go from -7 to +3, that's a distance of 10. So we know then that the amplitude should be 5, right? Because it would cut that distance in half. And so it should be at the halfway point. So -7 to -2 is 5, and -2 to +3 is 5, so that works out. So this guy here is going to be y equals -2. The amplitude, we've actually already talked about kind of subtly. The amplitude, the radius, is what we've been calling it in class, but on the graph, we often call it the amplitude, is going to be 5, because we know the distance between -7 and +3 is 10. And so half of that is going to be our radius or our amplitude. So we've got an amplitude of 5. And if we wanted to find this formula, check out what happens. We know that the formula is going to be f of x, only x because they've used x here, right? So they've named this x, so we're just going to use it as x. F of x is going to be the radius times the sine of bx, whoopsie, plus a. Okay, this is the general form that we've been using. Okay, we can start to fill some of this in. Clearly, the radius is 5 because the amplitude is 5. Okay, the vertical shift is going to be just wherever the midline is, so that's -2. But what we don't know yet is what is b. So let's talk about how to find that. I'll change pens real quick so that we can see that. So if we want to figure out what is b, we know that 2 pi over b is going to be the period. And we know that the period is 4.2. So that means a little algebra would get us that b is equal to 2 pi over 4.2. We can either do the actual calculation there, that's fine, or we can just leave it as 2 pi over 4.2. I don't actually care. So I'm going to put 2 pi over 4.2 right here. And this would be the function that we're looking for. That would be the formula for this function. All we have to figure out is what is the radius, what's the speed, what's the vertical shift, and then we've got it. Okay, so that's pretty simple. Okay, so I'm going to leave things there. This is hopefully a pretty short one, and we'll give you a chance to finish up your Module 7 and 8 homework assignment, and give you a chance to think about all those things before we get into class on Monday. Monday, we're going to start talking about Module 7 Investigation 8, number 2. If you want to take a look at that before class, you're welcome to do that. We're going to save our discussion of Modules 5 and 6 work until the second day of next week. So anyway, have a good weekend. Happy Halloween. Hope you enjoyed my ridiculous video, and I will talk to you soon.